Hello everyone, welcome to the fourth module and also to the week 4 of this course on microsensors and nanosensors. In this module, we will be talking about interface circuit required for the sensors that we are going to discuss from the fifth module. Okay. Till now, we have seen the basic introduction, classification of sensors, its physical characteristic including static and dynamic characteristics, followed by some principle of sensing including some capacitive, piezoelectric, pyroelectric, inductive, resistive, etc. Okay. So, what do we understand by interface circuit and why it is required? Okay. Let us understand this with this classic example. We have a sensor, we have some input stimuli which has to be fed to a load device. This load device can be a simple, say, DAC, okay, data acquisition system, okay, or it can be directly be fed into a microcontroller which is having a DAC integrated into it, okay. So, this sensor has to be, the data output of the sensor has to be fed into this DAC, okay. I am calling this for the time being as load, okay. The data from the sensor can be either in the form of change in resistance or in the form of change in current, okay, or in the form of change in voltage, okay. The level of this current change or the voltage change can be so low that it cannot be fed to this load device, or there can be a condition where this load device will not accept the current format of this sensor. Say the data output of the sensor is in the form of current, while this load device can only accept voltage at its input terminal, okay. That is why we say that we have to condition this signal which is coming out of this sensor, and that is mostly achieved by this interface circuit or the signal conditioning circuit of a sensor system, okay. So, that is why I mentioned that the signal from the sensor has to be conditioned before it is fed into the processing device or a load, as I have mentioned that this load is nothing but, say, a DAC card, okay. This load will of course need this signal in the form of current or mostly in the form of voltage, okay. So, let us understand the basic requirements of this interface circuit, what it can be, or actually this is the requirement of the sensor as well as of the load. So, this interface circuit is acting as a slave which has to fulfill its two masters, okay. The two masters are basically the sensor and the load device, okay. The requirements are like we may need an amplifier to amplify the signal that is coming out of this sensor. To operate this sensor, say for example, if it is an active sensor, we may need the external power supply or some kind of signal conditioning to its for its operation, okay. So, we may need some excitation circuit also for its operation, okay. Then we may require a current to voltage converter if the output of the sensor is in the form of current and the input of the load is in the form of voltage, okay. Similarly, we may need a voltage to current converter if the output of the sensor is in the form of voltage, while the load can only accept signals in the form of current, okay. Similarly, some sensors only generate charge, okay. However, this load circuit or the load device cannot accept this charge output or change in charge output. So, we have to have a charge to voltage converter, okay, so that it can be fed into the load, okay. Similarly, we need ADCs mostly, but with ADC we have some DAC also. So, ADC is nothing but analog to digital converter, and similarly we have a digital to analog converter that is required for these sensors, okay. Then once this data is acquired, we may need some signal conditioning circuit for data transmission, faithful data transmission, okay. And apart from that, we may also require some noise suppression strategies. Say for example, a simple bypass capacitor can be used for this noise suppression, or you may have some sophisticated circuit to condition this noise or to suppress this noise or minimize this noise, or sometime you may eliminate it also depending on what kind of noise we have. Okay, so you may need some strategies or in the form of interface circuit to minimize that. Okay, we'll see these requirements, but we'll see them, some of them at least, in this 5 lectures that we are going to cover in this module. Okay, but before we proceed, we should also understand the input and output impedance of sensor as well as the interface circuit, because the output of the sensor or the output impedance of the sensor will see actually the input impedance of the interface circuit, right? So we have to match them, okay, for faithful data transmission, so or better data transmission. So we'll see what is this input impedance and output impedance that I am talking about, and then we will see amplifier and other things. Okay, just see this example. Okay, I have a sensor and I have this interface circuit in the form of just equivalent model, which can be simply say a simple RC circuit in the parallel. Okay, now the input impedance is shown by how much the circuit load the sensor. Okay, because ultimately, even if you are not attaching the load device, this interface circuit is going to be a load at the output of the sensor, right? So the input impedance is shown by how much the circuit loads the sensor. Okay, and the input of a circuit is modeled as a parallel connection of input resistance R and input capacitance C. Okay, the complex input impedance can be represented by simply Z equal to R by 1 j omega RC, where omega is your circular frequency and j is iota or the imaginary unit, we all know. Okay, at very low frequencies, a circuit having a relatively low input impedance and resistance has an input impedance which is always or almost equal to, if what I am talking is, if say this omega tends to 0, okay, what will be the input impedance of this? Okay, when this tends to 0, this Z is almost equal to R, right? So basically you are having only resistive component in this complex impedance. All right, whenever an input impedance of a circuit is considered, the output impedance of the sensor must be taken into account, because your input impedance of the circuit will see the output impedance of the sensor, right? Say a simple example can be a two-terminal device. Say if this is a sensor, okay, I am writing it as a 2-port network. Okay, this is input, this is your output. Say there is some impedance of this, okay, and your circuit will be attached to this, right? So the input impedance, say if this is the input impedance of this circuit, okay, it has to be matched well with the output impedance of the sensor. Okay, that's why I am mentioning again and again that whenever an input impedance of a circuit is considered, the output impedance of the sensor has to be taken into consideration. Okay, say if the sensor is capacitive, the sensor's capacitance must be connected in parallel with the circuit's input capacitance. This will help in defining the frequency response, particularly at the input stage of the device. Okay, something like this I am talking about. Okay, right? In this case, this V in can be written as this E, okay, into Z in by Z in plus Z out, where this Z out is nothing but the output impedance of the sensor. This is output impedance of the sensor, while this Z in is basically the input impedance of the circuit. Okay, so do not get confused between the Z in and Z out, because we are going to use this terminology over these 5 lectures. Okay, so Z in is basically input impedance of the circuit, while Z out is the output impedance of the sensor. Okay, now once we understand this input and output impedance, okay, let us also understand the equivalent circuit of the sensor. Okay, if you know the equivalent circuit of your sensor, defining the interface circuit becomes easier task. Okay, so it helps basically in analyzing the frequency response and the phase lag of the sensor interface combination. Okay, say a capacitive detector can be modeled as a pure capacitive capacitance which is connected with the input impedance of the circuit. Okay, however, it can also be modeled as capacitance in parallel with the resistance depending on the sensor. Okay, of course this has to be connected in a parallel fashion with the Zin, which is the input impedance of the interface circuit. Okay, another example can be a piezoelectric sensor which can be represented by a very high resistance which is of the order of say 10 power 11 ohm, okay, which is shunted by a capacitance in the range of 10 picofarad. Okay, similarly for pyroelectric devices also we have equivalent circuit. Okay, we will see when we will discuss the occupancy sensors and infrared sensors. Okay, now to illustrate the importance of the input impedance characteristic, let us consider a purely resistive sensor which is connected to input impedance. Okay, the circuit's input voltage as a function of frequency can simply be expressed for this resistive kind of device as V is equal to this E, or the small e that you have just seen, divided by under root 1 plus f by fc whole square, where this fc is the corner frequency and can be represented by 1 by 2 pi RC, right. Please note that this fc or the corner frequency is the frequency where the amplitude drops by 3 dB. Okay. So once I understood this input and output impedances of the sensor, let us understand the amplifiers, which is the first stage which sees the output from the sensor. Okay, which has to do amplification before it is fed to the next stage. Okay, as I have mentioned earlier also that most of the sensors, particularly the passive sensors, generate very low level of current because you are not having any external bias to this sensor. So you cannot expect that there will be in situ amplification. Okay, so mostly the passive sensors generate very weak signals, and you do not expect much from the active sensors also because the generation of the electric parameters may be in the form of current or voltage is also not very high for those kind of devices also. Okay, the magnitude of these sensors is of the order of say nanovolt, microvolt, and sometime in picoamp or nanoamp. Okay, and that is very common when we discuss this microsensors as well as the nanosensors. Okay, so standard electronic data processors including ADCs, frequency modulators, data recorders, DAC or anything require input signals of a good amount of magnitude, few volts or at least few millivolts to some if you talk in current some milliamp or some amp. Okay, so basically the output from this sensor cannot be fed into the next stage, maybe a data processor step or say data acquisition step. Okay, therefore you need amplification. Okay, the amplification has to be made with gain requirement of say 100x or 100kx also. Okay, and current gain of also of even higher order. Okay, now there are several standard configuration of amplifier that might be useful for amplifying the signals which is generated by different sensors, and we may discuss specific amplification process for specific sensor. Okay, but in this module we are going to discuss in general the amplification process and amplifiers available in general. Okay, you can construct of course a plethora of amplifier configuration. Okay, these amplifiers may be built of a discrete component, for example some diode or transistors or other components. However, The amplifiers are frequently composed of standard building block, for example, a simple op-amp or instrumentation amplifier that we are going to discuss after some time. But for instrumentation amplifiers also you may need op-amp or operational amplifier. So what we will do is we'll see some basic behavior of an operational amplifier or basic construction of an operational amplifier, and how these op-amps can be used for various functionalities, okay, by just simply changing the passive component around it, okay. So let us see the basic properties of these op-amps, okay. For this op-amp you have two terminals. You have a non-inverting terminal or you have a inverting terminal. Apart from that you have 2 points through which you can give it a biasing, okay. So this device or this amplifier, okay, has a very high input resistance in the range of mega ohm to some giga ohm, okay. However, the output resistance is very low, okay, in the range of some few ohm, okay. This kind of behavior is, or this kind of characteristic is desirable for these amplifiers, because if it has a very high input impedance or high input resistance, what it is going to do is it is not going to withdraw any current from your power supply, okay. So basically it is not going to load the existing circuitry, okay, or existing system, okay. This op-amps has ability to drive all kind of loads including capacitive loads, okay. Input offset voltage is very low, okay. We will see what is input offset voltage, okay. Mostly it is of the order of a microvolt, okay. And the bias current, input bias current is also very low, or it is of the order of say picoamp or sometime even less than that, okay. The open loop gain of this amplifier is also very high, okay. So usually you can expect that minimum of 10 to the power 4 open loop gain for these devices, and even it can be more than 10 power 6, okay. These devices op-amps also have a high common mode rejection ratio or CMRR. It means that this amplifier suppresses the in phase equal magnitude input signals which is applied to both the input, okay. So basically when you have this op-amp in operation, you can expect that some kind of noise is generated at both the input, okay. And this is noise signal is basically what I am trying to say is, I am trying to convey is basically common to both the inputs, okay. But this op-amp has very good high common mode rejection ratio or CMRR. It means that it will reject any common signals, or this common signal is nothing but this noise. So basically it has better characteristic in terms of rejecting the noise at the input terminals, okay. Therefore, it has, you can consider that it has overall very low noise. Also, the intrinsic noise in this system are not very high, okay. They are also very less, okay. The good thing about op-amp is that its operating frequency range is quite high, okay. So you can operate your even if your sensor is operating in low frequency range, or even it is operating at high frequency range, basically you can deploy this op-amp for amplification, okay. Then it has low sensitivity towards the variation in the power supply voltage, okay. We want that there should not be any variation due to the power supply change, okay. However, of course this is not an ideal device, so it has little tendency to change with the power supply voltage, but that is minimalistic, okay. So a high common mode rejection ratio and low intrinsic noise, apart from other advantages including the high open loop gain that I have just mentioned, make it an ideal amplification system for our sensors that we are going to discuss in this course, okay. Apart from this, it is also very stable in the ambient, particularly with the change in relative humidity or change in temperature around it, okay. So when I say high open loop gain, I mean to say this, okay. this V out is equal to V in into AOL. This is the common signal that I was talking about. Okay. So if you see this curve, this shows the open loop gain versus frequency, and you can clearly see that open loop gain is falling with the frequency. Okay. It doesn't only fall with frequency, but it also changes, or this AOL is susceptible to change in temperature, change in relative humidity condition, and other external factors. Okay. So mostly you will find that these amplifiers do not operate in open loop condition, and mostly we have closed loop conditions used for this. Okay. And this reason, this blue line shows the closed loop gain. Okay, the closed loop gain. Alright. So AOL of the op amp is always specified but is not a very stable parameter, and its frequency dependency is shown over here. Apart from this, I have mentioned that it is also susceptible to change in temperature and change in other ambient parameters, okay, including the power supply fluctuation. Okay. So therefore, this op amps is rarely used with the open loop condition. Okay, because the high open loop gain can result in the circuit instability and a strong temperature drift, which will incur lot of noise in the system. Okay, if the open loop gain is, say for example 10⁵, the input voltage drift of 10 microvolt can cause the output drift of the order of say 1 volt or so. Okay, so you can understand the magnitude change that appears in the output when there is a slight change in the input also. Okay. So that's why the closed loop gain is very crucial for op amps. Okay. And to justify that, we have a GBP or GBW, which is known as gain bandwidth product. Okay. So the ability of the op amp to amplify small magnitude high frequency signal is specified by gain bandwidth product. Okay, just have a look on this. What I mean to say, that this op amp can amplify even a small magnitude signals that is coming out of sensor. Even it is at high frequency, it can magnify it, okay, or it can amplify it. Okay, and it is mostly limited by its GBW or gain bandwidth product. Okay, this GBW is equal to frequency f1, as you can see over here, where the gain becomes actually unity. Okay, and please note that above this particular frequency, this amplifier cannot amplify. Okay, so this is the limiting factor. Okay, so and if you see this configuration, this is the closed loop gain, which is very stable, although it is much lower as compared to open loop gain, and actually the ratio of AO by A is greater than 100 is desired for better operation of the sensor, and even for very stable operation you want AO by or open loop gain divided by the closed loop gain, say around greater than 1000. Okay. So let us see that how this op amp, you know, can be connected in various configuration for various output. Okay, this is a basic inverting amplifier configuration. Okay, you can see that there is a feedback resistance RF, and this input is supplied to this negative terminal, where this Ri is the resistance in between this V in and the negative value. Okay, so there is a concept of virtual ground, okay, which suggests that this potential and this potential of this op amp will be 0, or there is no current actually flowing into the op amp, right. So if you see this configuration, okay, this AV or the gain of this amplifier will be V out by V in, which is equal to minus RF by Ri. Okay, this is minus RF by Ri, where RF is this feedback resistance and Ri is this resistance. Okay. Similarly, there is a non-inverting amplifier which can be made, or this op amp can be configured into the non-inverting configuration. Okay. The output or the gain of this kind of non-inverting configuration of this op amp can be written as AV equal to 1 plus R1 by R2, or if it is RF, feedback resistance, 1 plus RF by R2, right. Please note that the name inverting and non-inverting is coming from this sign. So this is negative, so it is basically inverting, okay, and this is a non-inverting, okay, right. So accordingly you have applied signals to this negative terminal and to this positive terminal, okay. So this is a basic inverting and non-inverting amplifiers configuration. Now this op amp can also be used as a voltage comparator, okay. This is a simple voltage comparator structure where this output can be written as, depending on the signal, as this value, okay. Then this op amp can also be used as voltage follower. We will see what is voltage follower after some time, but you can understand this as a configuration in which the output and this output voltage follow the input voltage, okay, or the input, okay. Basically both are same, but what is its requirement we will see in some time, okay. Usually the gain of this voltage follower is 1, okay, or very near to 1, okay, and you can understand this as a current amplifier, not a voltage amplifier, okay. Now it can also be used as a summing amplifier to sum up the signals. Say for example, this is a configuration where a simple op amp has been used as a summing amplifier. You have 3 signals V1, V2 and V3 applied through the resistance R1, R2 and R3, and RF is the common feedback resistance, okay. If you calculate, the V out will be equal to minus V1 into RF by R1 plus V2 RF by R2 plus V3 RF by R3 and so on. If you have more number of resistance, say you have this R4 and V4, you have V out as minus this value plus V4 into RF by R4, right, and that is why its name is summing amplifier, okay. Then it can also be used as a differential amplifier, okay. In this configuration, if you see, the output voltage is equal to R2 by R1 into V2 minus V1, where V2 and V1 are the two voltages which we want to subtract from each other, okay. This is the difference amplifier, okay. Then I may configure this op amp using a capacitance as a integrating amplifier, okay. So in this integrating amplifier, in place of resistance, what I am placing in the feedback is a capacitance basically, okay. Other configurations remain same. So you have a V in which is connected through this R to this virtual ground, and you have a feedback in the form of the capacitance, okay, and the V out for this kind of configuration is nothing but this is equal to minus 1 by RC under root the V in data, okay, V in into dt, fine. Now if you just replace this capacitance by resistance and resistance by capacitance, you can actually make a differentiating amplifier, okay. So the output of such kind of configuration is equal to minus RC into dV in by dt, where V in is the input voltage applied at this end, okay. So we have seen that this op amp can be used as a summing amplifier, it can be used to find the difference, okay. It can also be used for integrating the input voltage, okay, and it can also be used for differentiating the input, okay. So the output in this configuration where capacitance has been, this resistance has been replaced by capacitance and capacitance has been replaced by resistance in an integrator circuit, okay. I have this V out as minus RC dVn by dt. So basically this V out is directly proportional to dV out by dt, and you are getting the differential value, okay. Similarly, it can also be used for current to voltage conversion. This is one example. Okay, you have a I in flowing into this amplifier, and R, the output is nothing but minus I in into R. Okay. Now, for such kind of voltage to current conversion, you cannot put this IL directly over here. Okay, this IL is which is flowing through this branch. Okay, and this IL is nothing but V in by R. Okay, V in is here. So, voltage follower that we were about to discuss, but we have not. Okay, voltage follower is actually very important circuit component or a part of this interface circuit, which is basically used as a impedance converter. Okay, so impedance converter from high impedance to low impedance value. Okay. So, it is basically, as I have mentioned earlier also, that it is basically a current amplifier and can be used as a impedance converter from high value to low value. Okay. So, a typical follower has high input impedance and low output impedance, and a good follower has a voltage gain very close to unity and a high current gain. Okay. That is why I mentioned that the output voltage actually follow the input voltage. Okay, because the gain is almost equal to 1. So, its high input and low output impedance make it very important for interfacing between many sensors and signal processing devices. Okay, basically what is happening is the Z out from the sensor, okay, has to be matched with Z in of the interface circuit. Okay. However, in turn this has to be matched with the load resistance input. Okay. So, I am calling it say Z bar input. Okay, or this Z out from this has to be matched with Z bar input of the load. Okay. That is why you have to do lot of impedance matching. Okay. Therefore, I mentioned that its high input and low output impedance make it very important for interfacing between sensors and signal processing devices, including the microprocessor and DAC. Okay. When a follower connected to a sensor, it makes a very little effect on the sensor's performance. Okay. Therefore, it provides a kind of buffering function between the sensor and the load. Because it can have a very high input impedance, okay, it is actually not loading your sensor, right. So, therefore, I mentioned that it actually acts as a buffer. Okay. For the current generating sensor, the input bias current of the follower must be at least 100 times smaller than the sensor's current. This is very important while you design this voltage follower circuit. Okay. Now, once you have understood this voltage follower, I am ready for this impedance matching kind of critical problems. Okay. Now, our amplification is not yet done. Okay. I have just learnt a simple op amp, but I have not seen the actual amplifiers that can be built out of this op amp. Okay. So, in the next class what we will do is we will discuss the instrumentation amplifier, okay, so that we have some basic understanding of the amplification that is required in this kind of sensors. Alright. So, with this we will close this lecture 1. We will meet again in second lecture. Thank you.